Let's talk now in more detail about average speeds. In our previous video, you saw a graph of a speed distribution function for oxygen molecules at standard temperature and pressure. And what you can do is use the equation for that speed distribution function to come up with equations that allow you to calculate average speeds. This would require you to do some calculus, so I'm not going to go through the calculus that's going to show where these equations come from. I'm just going to put up the equations that allow us to calculate average speeds. There are different ways that you can measure an average, and we're going to take a look at 3 different ways in this slide. The first way that we could look at the average speed is by determining what's called the most probable speed, which would be the peak in the speed distribution function. The most probable speed is equal to the square root of 2RT over capital M, where capital M represents the molar mass of your gas in units of kilograms per mole. Another way that you can calculate the average is just the straight up numerical average speed. It's important to notice that the most probable speed, that is the peak in the distribution, is not the average speed, because if you were to look back at the speed distribution function, what you notice is that this distribution function is not a perfectly symmetric bell curve. There is a tailing to it. And so the most probable speed here at the peak is not dead center on this. That's not going to be what the average is. The average is kind of where the dead center is, and that would be a little bit higher in velocity due to this tailing that you have here. The average speed is calculated by taking the square root of 8RT divided by pi and the molar mass of the gas. A third way that you can measure the speed or calculate the speed of a gas is by calculating what's called the root mean squared speed, or the RMS speed. And this is a weighted average speed. And this value has a lot of physical importance if we were to calculate, let's say, kinetic energy. When you calculate kinetic energy from physics, you have an equation that says kinetic energy is equal to 1/2 mv squared, where v is the velocity. And the velocity that you would use would be the root mean squared velocity if you have, let's say, an ensemble of gas particles. So being able to have an equation for root mean squared speed is important. This weighted average is what's used when you're determining kinetic energies of gases. The equation for calculating root mean squared speed is the square root of 3RT over the molar mass. And again, I will emphasize here, M represents the molar mass, but it represents the molar mass in units of kilograms per mole, not grams per mole. And we'll see why that is when we take a look at an example now, where we will calculate the average speed UAVG for ammonia at 298 Kelvin. One other thing that I'll mention before we get into this example is that there are 3 different ways that you can calculate the average speed. And right, these are just 3 different ways that it can be found. And in a problem, I would very clearly specify which one of the 3 I would want you to use. And since this problem specifies that we want UAVG, then this is the equation that we're going to want to use. Square root of 8RT over pi m. So we'll go on to a blank slide and do the calculation now. I'll start by writing out the equation. U average is equal to the square root of 8RT over pi m. And now we'll go ahead and plug in the numbers. And it's going to be really important to take a very careful look at units. We'll now say U average is equal to the square root of 8 times R. When we're dealing with speeds or energies or anything of that sort, we want to make sure that we're using the big value of R. We want to use 8.314 because the units that contain joules will be very important for us when finding an average speed. So 8.314 joules per mole per Kelvin. Temperature we're told is 298 K over pi. And then the molar mass of ammonia is 17 grams per mole. But we want to convert that to kilograms per mole. So you're going to divide by 1,000 because 1 kilogram is 1,000 grams. All right. Now let's take a very careful look at the units. And to see how they all cancel, there's one more thing that needs to be added here. And that is this. When we're talking about joules, this is a unit that is comprised of many other units that are kind of put together. And so let's decompose what a joule represents. So a very important note here is 1 joule is the same thing as 1 kilogram meters squared per second squared. And by writing it out like this, we start to see why the units of joules are so important when finding an average speed. Because if we want meters per second, right, joules contains units that involve meters squared per second squared, right? Additionally, writing this out helps us to see why the molar mass has to be in kilograms per mole, because the units of joules contain a mass unit of kilograms. With all of that in mind, let's substitute that in for our units, and then we'll see how the units cancel out and how we get the correct answer here. The average speed is, I'm not going to really change anything here, just the unit. 8 times 8.314, and then instead of writing joules per mole per Kelvin, instead of writing joules, I'm going to say kilogram meters squared per second squared, that's joules per mole per Kelvin, times the temperature of 298 K over pi, and then the molar mass, and 17 divided by 1,000, I'm just going to rewrite that as 0.017 kilograms per mole. Now, for the units. We'll first take a look at how Kelvin cancels Kelvin, and then we also see why you have to have kilograms per mole as the molar mass, right? Because the kilograms in the molar mass cancels the kilograms from R, and the per mole in the molar mass cancels the per mole from R. We're left with meters squared per second squared, and notice that we're taking the square root of this whole number, right? So that means you have to take the square root of the units. So the square root of meters squared per second squared is just meters per second. That's what we're trying to find here is a speed. So it should have that kind of a units. And when you plug the numbers into your calculator, the value that you get for the average speed of ammonia at 298 Kelvin will be 609 meters per second. Now, I recognize that we don't often deal with units of meters per second, right? We often, in our everyday lives, deal with imperial units like miles per hour. And so to give you an idea of what this speed would be in miles per hour, if you were to convert it, you would find that the average speed of ammonia molecules at 298 K is 1,365 miles per hour. So these gas particles are traveling very quickly, even at just room temperature. There's enough thermal energy at room temperature to allow the molecules to travel at 609 meters per second or at 1,365 miles an hour. Let's take a look at another example that deals with average speeds. So here we have, again, our 4 different identical 1-liter flasks, each containing 1 mole of a different gas at 25 C in 1 atmosphere. And I want you to determine which of the samples has the smallest average URMS. And I've included the equation for URMS here. And I want you to determine which of the samples has the smallest average root mean squared speed. So take a moment to figure that out. And on the other side of the question, we'll go over it together. All right, once again, it's important to take a look at the equation to see how the value that you're interested in, right, in this case the URMS, relates to other variables that we're dealing with in the problem. So in this problem, all the gases are at the same temperature, right? So T is constant, and so we don't have to worry about that. But one thing that is different between the samples is the molar mass. And what we recognize here is that in the URMS equation, we're dividing by molar mass, meaning that we've set up an inverse type of proportionality here, right? So if you want a small value for URMS, then you need to divide by a really big molar mass. So for a small URMS, you're going to want to make a big molar mass. And the sample that has the smallest average RMS will be the sample that has the biggest molar mass. In this case, it would be the Cl2. And this kind of makes sense when you think about it, right? Like, the heavier the molecule, the slower it's going to travel, right? Imagine you're going to go and run a mile, and then imagine running a mile with a backpack that has like 200 pounds of weight on it, right? If you strap 200 pounds of weight to you, you're going to travel a lot slower, right? Increasing the mass is going to decrease the average speed. So it is helpful to think about how you can analyze these equations in order to find out that information. And it kind of confirms what you might figure based on intuition from things that you encounter in your everyday life. That brings us to the end of this video. And in our next video, we'll get even more practice dealing with speed distributions and average speed equations.